Hi guys, today we're learning about this is the second slide of quantum physics part 2. This is wave versus a particle. So if you haven't watched part 1, then go ahead and watch it right now. It introduces the basics of quantum physics, and yeah, let's get started. Okay, so start with continuation of the last part. What has quantum mechanics given us? So you're maybe wondering, like, why should I learn this? It has nothing to do with our real world. So basically, quantum mechanics has given us computers. You have LEDs, that light in your house. That's quantum mechanics. Lasers, mini computers, microcomputers, particle accelerators, cameras, stuff like that. So quantum mechanics is important in our life, and if we don't have that, we won't really be able to have all these advanced technologies. Okay, so let's start with the study of quantum mechanics. So quantum mechanics is the study of atoms, protons, neutrons, electrons, photons, stuff like that. It's the study of tiny particles. But wait, you may have learned that electrons, protons, and subatomic particles, basically. You may have learned that those were particles. Like, you may have learned that, electrons are like a tiny subatomic particle, protons, neutrons, but in reality, quantum mechanics, we describe things a little bit differently. So basically, these electrons, protons, and neutrons can be described as both a particle and a wave. So you can say that this function right here can be described as a wave, or you can describe it as a particle. So we have the quantum realm in our world. So as you can see, subatomic particles in our world, they're described as particles because we can see them and we can see them with microscopes and stuff. But in the quantum realm, they're described by mathematical functions called waves, which we can't really see. We have to this is like a mathematical visualization of what a particle would look like in a quantum realm. So basically, we can't really see these waves, but we can perform mathematical functions on them, such as we can figure out the position, momentum, probability distribution, stuff like that. So yeah. So let's start with our first concept in quantum mechanics. So this is called wave-particle duality. So this is basically saying that you can describe a particle as a wave and a particle. Like an electron, like I said, can be both described as a wave and a particle. This is basically evidence of how quantum realms exist, because even though we can't see them, we can still see its effects on our world. So yeah, we can see that, and then we can also see a wave as a particle or a wave, which I'll explain later. So you may be asking, if we can't see the particle as a wave, how do we know it exists? Like, how do we know waves exist? But, well, we have the double slit experiment performed by Thomas Young and Sir Isaac Newton. By the way, if you're wondering, Sir Isaac Newton, he got knighted by the King and Queen of England at that time, which is why we call him Sir Isaac Newton, not just Isaac Newton. So just a little fact. So yeah, we have that. So basically, let me show you. So if you take a light source, like a laser beam or something, and then you shine it on a board that has two slits in it, you will see it on the very back wall behind the board. What would you expect to see? Well, we know light is a wave. Hopefully we know that. And the light's going to go through each slit and diffuse to make sort of a new wave, as you can see from here. So we have, in this image, we have the, don't worry about the electron beam. I'm going to pretend this is a laser. So we have the laser shining through. And so yeah, right here we have the light source, which is shining through as waves, as you can see, because light is a wave. And then these two slits right here, it's going to diffuse and sort of make a new wave in each of the slits, and they're going to overlap, so they make a sort of a new wave. So once they overlap, as you can see here, there's some sections where they overlap, like here, right there, stuff like that. So once they overlap, they will either cancel out or they will amplify. So right here, you can see it on the back of the board. You see a light, dark, light, dark. So the light places are where the light is amplified because of the overlapping, and the dark places are where they cancel out. So This process creates a pattern of light on the very back. This is because when the waves overlap, they will amplify the light or they will cancel it out. We shouldn't really be surprised by this effect because this is not the quantum part of the experiment, because light is a wave. This is typical wave behavior where it's going to diffuse going through each hole. So if you have a light, you shine it through this light source, you shine it through this board with two slits. It's going to make a new wave on each side right here, and then it's going to form a pattern on the very back wall on the screen. So that's typical wave behavior. But what do you think is going to happen if we try this with atoms? Instead of having a light source, imagine we had an atom gun, like it says right here, an electron beam gun. What do you think is going to happen? So when I first heard about this, I thought it would look something like this image at the bottom, where you shoot atoms through the slits, and of course they're just gonna bounce and hit the backboard. So wherever the slit's opened, it's just gonna clumper up over there. As you can see, a bunch of atoms are just lined up wherever the slits are. So that's typical like particle behavior, like sand or something. This could happen with sand or other small particles. But with an atom gun, this is proof that particles can also act like waves, because when Thomas Young tried this experiment, something different happened. Instead of showing this image right here, it showed the wave image, a typical wave behavior. So whenever he shot atoms, it went out like this. As I explained over here, it went out as waves, diffused, and then still formed sort of this pattern, where you have atoms in the middle and then side, 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 till it gets lighter and lighter. So how does this happen? Because if you're shooting atoms from right here, and then how does it appear? How does it appear to be over here? Because there's a wall in the middle, right here. How do atoms pass through this wall? Well, that's because they're not just particles; they're also waves. So they diffuse like this, as waves do, and then they can form this pattern on the back wall. So this is the quantum part. So yes, so this is proof that particles can be acted as waves, as you can see from this experiment. And just saying, waves can also be particles. So proof of this is like the black body radiation experiment. That's proof that waves can also act as particles, which was discovered by Max Planck. And Albert Einstein later refined this discovery with the photoelectric effect, which he got the Nobel Prize for. So, I mean, if you got the Nobel Prize for this, I'm assuming it's pretty important in physics, and it is, because this is saying that waves can act as particles and particles can act as waves. That's what wave-particle duality means. So all of these experiments and stuff can be wrapped in this concept called wave-particle duality, which is all just proof stating that a wave can act both like a wave, a particle, and a particle can act both like a wave and a particle, or like a particle and a wave, vice versa. So that's it for today's part. Thanks for watching. Like, subscribe, hit the notification bell if you want more parts to come in. Please give me 2,000 subs. And yeah, thanks for watching. Actually, yeah, just get me to 1,000 subs, please.